Hi everyone, my name is Thomas Kim. Today is October 28th, 2024. It is 11:46 a.m. Calculus, Early Transcendentals by James Stewart, 8th edition. This is one of my favorite calculus books. Calculus by Anton, 10th edition. I also like this book quite a lot. Thomas's Calculus, Early Transcendentals. This is 13th edition. In this book, Chapter 15, Multiple Integrals, Section 15.6, Moments and Centers of Mass. I assume you have read the text in this book. If you scroll down, you can find example 1, then example 2, we will learn how to compute centroid or center of mass. I also assume you have read Moments of Inertia in this part of the text. Then we'll be solving example 3, also example 4, then exercises. Open up Visual Studio Code, then open Topology 1. Here, click this 017 Moments of Inertia. Click this button, section 15.601.cpp. Hit enter. Ctrl B. I will close welcome window. Then I will drag and drop this PDF book. Click this sidebar. Then select outline. If you scroll down, select 15.6 Moments and Centers of Mass. Then close it. I assume you have read Moments and Centers of Mass, this part of the book. We will start with example 1. Arrange side by side. Here, I will copy and paste these things. Go up if you want to follow my current session. You need up-to-date CPP extensions. Then fold it up. Here, I will copy and paste this problem. I will arrange the text like this. I will zoom up, then I will read the problem. Find the center of mass of a solid of constant density, delta, bounded below by the disk r x squared plus y squared less than 4 in the plane c equals 0 and above by the paraboloid c equals 4 minus x squared minus y squared, figure 15.36. So this is figure 15.36. We want to find center of mass. Now I will arrange like this. Here, for the solve example 1 vector. Int main, copy this function name in the function main. Here, cpg display function name. We have to represent the coordinate system using cylindrical coordinates. enum rho theta c rho rho theta g of alpha 3. I will make it bigger. then like this. Oro R, VCTR 3D, semicolon, X component, rho times sin cosine theta, copy, paste, y component, sine theta, g component, g. So this vector R represents cylindrical to rectangular coordinates transformation. In this problem, constant density or density 1.0, then or mass, and we can use this coordinate transformation. Volume integral, don't miss semicolon. Density, we specify row limit. In this case, x squared plus y squared equals 4. Rho is the radius on xy plane. So it should run 0, 2.0. This is row limits. Then we can specify theta limit 2 times 5. Theta limits. Then we have to specify the limits for variable z. Z is variable. We have to use tuple. The value z changes from 0 on xy plane, then up to 4 minus x squared minus y squared. So we have to describe x squared minus y squared, or it can be 4 minus r squared. To represent this, we need to introduce rho r t OPR bar 2. Please note that we specified row limits first. Okay, row limits first, then theta limits. So this R is for row, this T is for theta. Then 4 minus R square. This is Z limits. This is Z lower limit. Z upper limit. Then we have to specify integration order. Dior. Our first parameter is rho. This order is defined here. So I can use rho, then follows theta limits. So underscore theta, then follows g limit, then underscore g. This represents integration order. In this book, if you scroll down, you can find the mass. The mass is 8 pi delta. So auto mass A 8 times pi times density. Algebraic answer from the textbook. To find the center of mass, we also need to compute first moment. We need to compute the balance with respect to xy plane, or in this problem, in the plane c equals 0 means xy plane, or m, xy, n. We use this coordinate system once again. This is first moment of mass, which represents balance with respect to xy plane. Here we multiply z. Z is the distance from a mass element to the, I would give line break here, xy plane. In this case, then this book also gives first moment with respect to xy plane like this. Answer from the textbook. Or mxy a 32 times 5 times density over 3. I would say algebraic answer from the textbook. SED, C out, M, mass N, mass N, NL, copy, paste. I will denote it mass A, then NL. Cut. I will paste it here. Then scroll down, paste. It should be MXYA, MXYA, MXYN, MXYN. Now, auto center A array 0.0, 0.0. Because in this figure, center of mass is symmetric with respect to z-axis. M xy a over mass a 0.0, 0.0 because the center of mass is symmetric with respect to z-axis. The algebraic answer from the textbook. Auto center n array 0.0, 0.0 m xy n over mass n. I will copy this, copy, paste. Then center A, center B, Open up any compiler. CD 017 Moments of Inertia, dir Clang++, SCD, C++ 20, SEC 15, 601.cpp, LTBB 12, OC.exe, hit enter. I think I made typo here. It should be center N. We revealed CLSC. So everything works perfectly. I will fix N. We will try with the Intel compiler CD 017 Moments of Inertia ICX CL QSED C++ 20 EHSC. I will use MD switch OD sec 15 601.cpp. I will also use fno sickle oi.exe, hit enter. I will copy this string, control home, then I will overwrite. Let's check i.exe, hit enter. It works perfectly. Also, I would copy this, then paste it here. We can also try G++ compiler, CLSC, CLSG. Everything works perfectly. Control home. I will fold it up. Copy this up to this point. Copy, paste. Scroll up. Here, Jacobian. Copy this. Paste it here. Scroll up. Previously, we defined 3D vector. Using this 3D vector, we integrated using volume integral. We will turn it to Jacobian matrix. Cine, create Jacobian matrix. Now I will represent it as J. J represents cylindrical rectangular coordinate transformation. We are now using Jacobian matrix. Scroll down. We cannot use volume integral. Instead, all dv j differential. This v represent dv, the volume differential, sqrt, absolute value, dt, determinant, Jacobian transpose, Jacobian. This is matrix product. If J is n by n square matrix, dv, the volume differential, is returned. If J is m by n non-square matrix, then I made mistake here. In this case, we don't need this. This is good enough. If J is m by n non-square matrix, then dv or surface element, surface differential, is returned. In our case, we are using 3 independent variables and 3 equations. 3 independent variables with 3 equations. So this dv represent this. Then we can use sin integral. We provide dv volume element. Then sin integral, we have to multiply dv volume element. So the remainder is the same. I will copy, pasted it here. With this, we build again. CLS G. So in this function, we used vector calculus. In this function, we used Jacobian. The result should be the same. CLS G, it runs slow. So I will explain how to optimize. In this case, volume integral, internally it uses recursion. If you provide a pulse, then it does not use recursion. Instead, I can provide 8 segments for each dimension. In the same manner, we can use it also here, also here. So whenever you do integration, you can control performance. With this, I must made some mistake. Scroll up. I made a silly mistake. Here, I should remove this. Then rebuild CLS G. See, in example 1 vector, we computed using vector calculus. In example 1 Jacobian, we solved the same problem using Jacobian matrix. Now, scroll down. We have example 2. Scroll down. I will copy and paste it here. With solve example 2. CPG display function name. Copy the function header in the function main. I will disable this. I will arrange like this. Then find the centroid of the region in the first quadrant that is bounded above by the line y equals x and below by the parabola y equals x squared. So we want to find the centroid of this problem. Here, 어로 x, y, OPR bar 2, enum underscore x underscore y semicolon. I will define xy coordinate like this. 어로 r VCTR 3D x y. This represents xy plane in vector. I will let density 1.0. Then 어로 M N R surface integral. Don't miss semicolon here. I will indent. Density. Our variable x changes from 0 up to 1. So 0.0, 1.0. This represents x limits. Then our variable y changes. X equals 1 to x squared. So tuple in this graph, lower bound is x squared. We cannot use this. We take one parameter from x limits. So over xx, we say bar 1. This is equivalent to OPR bar 1. This is equivalent. So we say xx times xx. This represents x squared, the lower bound or limit for y. Then y equals x. So xx. This is y limits. Then this is differential order. X limits comes first. So underscore x. Then follows y limit underscore y. So this is surface integral. See, in this problem, the mass is 1 over 6. Okay, this is the mass. The mass is 1 over 6. Or MA 1.06. Algebraic answer from the textbook. Then SED, C out, MANL. Copy, paste, MNMNNL. With this, we build again. CLSG. So we computed the mass of this area. Now I will copy this part, then paste it here. I will rename MY. Then copy once again, paste MX. Scroll up. Here, first moment with respect to y-axis or horizontal balance. Here, first moment of mass. I would say first moment of mass with respect to x-axis or vertical balance. I will introduce one more variable called yy. Scroll down. First moment of mass with respect to y-axis. With respect to y-axis, it represents horizontal balance, up or down, horizontal balance with respect to y-axis. So we need distance from y-axis to the mass point. This red point is called mass element. We need distance from y-axis to the mass element. This distance is obviously x. Now scroll down. First moment of mass with respect to x-axis or vertical balance. Now we want to measure vertical balance with respect to x-axis. We need distance from the mass element to the horizontal line. This is height, y. So we multiply y. Now scroll up. I will change the limit. In this case, I will use y limit. Here, y limits represent from 0 up to 1, this range. Then we draw horizontal line So this graph forms upper bound. This upper bound, the horizontal distance, this x should be represented with y. So this is square root y. The lower bound is y. The lower bound is yy. The upper bound is cnm square root yy. This is x limit. Now scroll down. In this case, x limit runs from 0 to 1. Y, the vertical distance from the mass element to the x-axis. Upper bound is x, lower bound is x square. So this is lower bound, this is upper bound. Now here MYA in this book, MY 1 over 12. MYA, MYA, MY, MY. Here MX 1 over 15. MX 1 over 15. MX, 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 MX. Now we build again CLS G. MA, MN, they are identical. MYA, MYN, they are obviously different. MXA, MXN, they are identical. This is very common mistake. Now go back. In case of MXN, MXN, this answer is correct because we specified x limits, then follows y limits, x limit, y limit. This stands for differential order. Now scroll up. MYN, MYN is wrong because we specified y limits, then follows x limit. But the differential order is wrong because we specified y limits first. It should be y, then follows x limits, so it should be x. With this, we build again CLS G. Now MYN computed correctly. Keeping differential order correctly is very important. Or we can use sapiens. In this case, we specify x, specify y. With this, we build again CLS G. Now everything works perfectly. From my experience, 3 or 4 mistakes I make related with the integral come from incorrectly defining integration order or differential order. If you right-click, go to definition, sapiens, we pass differential order to reverse sequence. That is, the I system of Homo sapiens is the reverse of the dior or the I system of the octopus. So, sapiens is reverse of dior. 3 or 4 mistakes I frequently make arise from incorrectly specifying the integration order. Please don't forget this. Now scroll down. Here, ortho, centroid, A, array, M, Y, A over M, A. Copy, paste, M, X over M, A. M, Y. The first moment represents balance with respect to y-axis or horizontal balance. So, the horizontal center of mass or x-center is related to mi over m. mx. The first moment represents balance with respect to x-axis or vertical balance. So, the vertical center of mass or y-center is related to mxm. Copy, paste. Centroid n, min over mn, mxn over mn. I will copy this, paste it here, then centroid A, centroid A, centroid N, centroid N. With this, we build again CLS J. So our numerical answer matches exactly the algebraic answer. Up to this point, we defined vector R on xy plane. Example 2 with vector. Copy this, copy, paste it here. Now this is without vector. Copy, paste, paste. Previously with the vector, now without vector. So we are solving the same problem. We just use vector. Now we do not use vector. Scroll up. We are not using vector. So we don't need xy plane. Instead, we use CNA integral. Copy. Here also CNA integral. Also CNA integral. So we removed all vector integration. With this, we will now use Clang compiler CLSC. Solve example 2 without vector works perfectly, as in with vector problem solving. Then why I prefer solving problems with vector? I would say this method works because we are using no transformation, i.e. rectangular coordinates. But when the problem becomes more complex, we have to consider coordinates transformation, which vector calculus handles behind the scene. If we go up in example 1 here, our example 1 is more complex. In this case, we used cylindrical to rectangular coordinate transformation. This represents cylindrical to rectangular coordinate transformation. Here, the vector are thus transformed behind the scene. If you scroll down, here, volume integral This handles dv, rho, d rho, d theta, dz behind the scene. Now scroll down. In example 1, Jacobian. To solve this problem, we now represented this figure using Jacobian matrix. This Jacobian matrix represents cylindrical to rectangular coordinates transformation. This Jacobian handles the volume differential element. So this dV is rho d rho dz. In this case, we simply use integral. This is scalar integration. When we do not use, in this example, vector calculus, we may use Jacobian matrix to do cylindrical to rectangular coordinate transformation. So we have to specify dV Jacobian differential with multiplication, the volume element. Also, the volume element. Understanding coordinate transformation is crucial to be successful advanced calculus. We will solve more problems later. I will discuss example 3 in my next episode. Also, example 4 in my next episode. Here, select this, click this button, exe 15601.cpp, hit enter. Control B, from here, Control Home, copy up to this point. Paste it here. I will close it. In this book, scroll down. In page 920, exercise 15.6, we will solve problems here. I will copy and paste it here. In the main, this is page 920. So, page 920. I will make it bigger. Problem 1. Find a center of mass. Find the center of mass of a thin plate of density delta equals 3, bounded by the lines x equals 0, y equals x, and the parabola y equals 2 minus x squared in the first quadrant. So this is our problem. Copy and paste it here. You have to read your problems very carefully. Bounded by the lines x equals 0, y equals x, and the parabola y equals 2 minus x squared in the first quadrants. Here, x equals 0 means y-axis. Also, in the first quadrants means x and y are greater than or equal to 0. X equals 0 means y-axis, not x-axis. You have to be extra careful. The density delta equals 3. So, overall density 3.0. Overall m n sin integral semicolon. We need overall x, y, OPL bar, 2, enumeration, underscore x, underscore y, I aligned like this. So we are computing mass. We need density, then in this problem, y equals 2 minus x squared and y equals x. We have to solve these two equations. From this to this equation, we substitute x. Then x squared plus x minus 2 equals 0. Then x plus 2 x minus 1 equals 0. We have x negative 2, x positive 1. In the first quadrant, suggests that x should be 1. When x is 1, y is 1. So 0.0, 1.0, x limits. Then tuple, we have to specify y limits. We have to draw picture. Try to picture in your mental image or draw out your pen and paper. Draw picture on your paper. XX is lower bound. 2 minus XX times XX. This is upper bound. I will explain. This is y equals x, the lower bound. This represents the upper bound. I will use like this. Then we have to specify sapiens integration order. This represents y limits. So underscore y, then x limit underscore x. This is our math. Then we copy this, paste it here. This is my first moment of mass with respect to y-axis or horizontal balance related to x-center. We multiply x. X is distance from the mass element to the y-axis. Copy, paste. Now, first moment of mass with respect to x-axis or vertical balance related to y-center. It should be mx. Y is distance from the mass element to the x-axis. Then auto centroid and array m, y, n, m, n, m, x, m. The answer in the book says centroid A, MA, MYA, MA, MXA, MA. Go up, auto, MA 5.0 over 4. I asked it to ChatGPT. Here, STD, C out, MA, MA, and there, M, N, M, N, N, L. Copy this, paste it here. I asked ChatGPT, auto, MYA 5.0 over 4. MIA, MIA, MIN, MIN. Copy this, paste it here. Auto MXA 19.0 over 5. MXA, MXA, MXN, MXN. Now copy this, paste it here, centroid A, centroid N, centroid A, centroid N. We build again. CLSC. Sorry, I forgot to copy this function name. We copy and paste it. We built wrong file. This is exe. Hit enter. So we missed defining XX. Scroll up here. Auto XX OPL bar 1. With this, we build again. CLSC. Here, I think I made mistake. This value is a 7.0 over 2. I asked ChatGPT to solve it. Copy. Also here. Also here. We build again. CLSC. So this is our numerical computation. This is answer from ChatGPT. Now let's move on to more challenging problem. Find the moments of inertia. I would copy and paste it here. Copy the problem, paste it here. I will disable it. Find the moments of inertia about the coordinate axis of a thin rectangular plate of constant density delta bounded by the lines x equals 3 and y equals 3 in the first quadrants. How can you solve such problem? I will make this problem more interesting. Auto I, xy, we create a lambda CPT number or function C density type. Then density type density. We are creating a lambda. I will make it smaller. Then auto my I y we capture lambda CPT number C ARG type with ARG type height semicolon enum underscore x underscore y semicolon auto x y OPL bar 2 we return CNA integral semicolon density times x times x squared distance from the mass element to the axis of rotation. In this case, y axis of rotation. X squared distance from mass element to y axis of rotation. Say squared distance x from the mass element to axis of rotation. Then 0.0 width. This is x limits. Copy paste. Height y limits. Then differential order we specified x limits first. So underscore x underscore y. Now copy this, paste it here, x, then y, Scared distance y from the mass element to the x-axis of rotation. Now I will fold it up. Here, return LCD tuple IY IX. Here, auto XY OPR bar 2. Auto density, we can say 2 times x plus 3 times y. Density of the rectangular plate. Auto IY IX. We call IXY. We pass density for double unit 1.0 unit for plus unit. I would say 4.0. Then auto width, height, array, unit, LCD, cout, I, Y, width, height. Then IY, width, height, NL, paste, IX, I missed this. Also this, NL. I will put carriage return. Also carriage return. With this, we build again. CPT. This is number or function. We build again. CLSC. So when 1 unit, when 2 unit, when 3 unit, when 4 unit, we computed moments of inertia. I will copy this problem, then paste. The above problem comes from a typical math textbook. Instead, I would suggest you that find moments of inertia about the coordinates of a thin rectangular plate of density like this, bounded by width, height. In the first quadrant, where width, height pairs are 1, 1, 2, 2, 3344. Solve the problem I suggested above. Keep solving. Provide me with numerical values for each pair of width, height. Let's compare with my answer. So 1 1 is correct. 2 2 is correct. 3 3 is correct. 4 4 is correct. Here I will change the display order. NL, NL. We build again. CLS, C. So these are my results. Your results match exactly with the calculations I provided. Each pair of moments of inertia, Ix and Iy, aligns perfectly with your values. This confirms the correctness of both our computations. So, ChatGPT successfully solved this problem. Now, I will copy my source code. This is my source code. How do you rate this C++ programming style?
Your C++ code demonstrates a strong grasp of modern C++ features, especially the use of templates and lambdas with parameter packs. Here's a breakdown of some highlights and considerations. Number 1. Use of lambdas and templates. You've employed lambda expressions to define Ix and Iy functions with template parameters, making it generic and adaptable to different density types and limits. The use of concepts like CPT, number or function C. Number C ensures type constraints that can enforce strict type requirements at compile time, aligning well with C+20 practices. 2. Functional programming style. The functional programming approach with lambdas is effective here, especially when dealing with mathematical operations and calculations. This keeps your code modular and reusable, where Ix and Iy are isolated and can independently handle different calculations as needed. 3. Structured binding and enum for readability. Using structured binding, AutoXY, OPRVAR2, and enums, core X and Y for axis definitions is elegant and improves readability. This is a good approach for working with symbolic expressions or variables. 4. Generic density handling. The design of IXC as a higher-order function that accepts different density functions showcases flexibility. This allows for easy swapping or modification of the density function without needing to modify the IY or IX functions, enhancing the code's modularity. 5. Looping over cases. The loop to calculate moments of inertia for various widths and heights is concise and neatly utilizes an array structure. This approach allows for easy adjustments if more dimensions need to be tested or added. Suggestions. 1. Error handling for edge cases. Consider handling cases where unit might be 0 or negative in future extensions. Although your example doesn't anticipate these, robust code typically considers all inputs. 2. Consistent naming conventions. While the names Ix and Iy are concise, using slightly more descriptive names like moment X or inertia X might make it clearer for someone reading the code without a physics background. 3. Comments for context. The inline comments help, but more detail on the purpose of each component, especially CNA integral and dior, might assist other developers in understanding your code faster. Function return type. The use of stat tuple IYIX as a return type works well for this context. However, in some cases, a struct with named fields could improve readability, especially if the codebase grows or additional quantities need to be returned in the future. Overall rating. I'd rate this programming style highly, around 8.55 tenths. It demonstrates a deep understanding of modern C++ capabilities with a clean, functional approach. Small refinements like more consistent naming and additional context comments could elevate readability, but the current code is robust, efficient, and well-structured for a scientific programming context.